Hello, and welcome back to the channel. Today, we're tackling a foundational technique for managing massive data volumes and user loads, how Twitter scaled with Sharding, a deep dive into real-world database partitioning. At its core, database sharding is a method for horizontally partitioning data. It involves splitting a very large database into smaller, more manageable, and faster parts, which we call shards. Each shard operates as an independent database instance, holding only a subset of the overall data. This technique is primarily employed to address the scalability limitations of a single database server. By distributing the data and the associated read/write load across multiple machines, Sharding significantly improves scalability, reduces the load on any single database server, and thereby enhances overall system performance. This approach is indispensable in high-scale systems such as Twitter, Uber, and Amazon, where handling billions of data points and millions of requests per second is a daily reality. It's important to note that shards can be either physical, meaning they reside on entirely separate server machines, or logical, where they might be distinct partitions within the same large database instance, though the former is more common for true horizontal scaling. When implementing sharding, several distinct strategies can be employed, each with its own advantages and use cases. Vertical sharding. This approach involves splitting the database by feature or module. For example, in a social media application, user profile data might reside in one database, shard, while messaging data lives in another and tweet data in a third. Each shard corresponds to a distinct functional area of the application. Horizontal sharding, or database sharding, this is arguably the most common and powerful type for scaling large datasets. Here, the database is split by rows. For instance, all users with IDs from A to M might be stored in Shard 1, while users with IDs from N to Z are in Shard 2. The key is that the schema remains identical across all shards. Only the data rows themselves are partitioned. This is the method Twitter famously adopted for its user timelines and other core data. Directory-based sharding. This strategy uses an external lookup service or router to map a specific piece of data, identified by a key, to its corresponding shard. When an application needs data, it first queries this directory service, which then tells it exactly which shard to connect to. This provides immense flexibility, but introduces an additional network hop and a potential single point of failure if the directory service isn't highly available. While offering immense scalability benefits, sharding introduces a new set of complex challenges that must be carefully considered during system design. Picking the right shard key. This is perhaps the most critical decision. The shard key, for example, user ID, region ID, tweet ID, determines how data is distributed. A poorly chosen shard key can lead to uneven data distribution, known as data skew, or hinder future scalability. Data skew. This occurs when one or more shards end up holding significantly more data or experiencing disproportionately higher traffic than others, effectively becoming a new bottleneck. This negates the benefits of sharding. Cross-shard joins are expensive. When data related to a single query spans across multiple shards, for example, joining user data from shard A with message data from shard B, performing these cross-shard joins becomes incredibly complex and resource-intensive. Good design aims to keep related data on the same shard to avoid such operations. Resharding is hard. As your data grows, you might need to add more shards or rebalance existing ones. This process, known as resharding, is notoriously difficult. It often requires migrating massive amounts of data and potentially refactoring significant parts of your application code to handle the new distribution. Planning for resharding from day one is crucial. Strong consistency is harder to guarantee across shards. Ensuring immediate, global consistency across independently operating shards can be a significant architectural challenge. While eventual consistency is often acceptable, scenarios requiring strong transactional consistency across multiple shards are complex to implement. Twitter provides one of the most compelling real-world examples of successful sharding. Around 2008, as Twitter's user base exploded, their original monolithic MySQL database architecture hit severe scaling limits. They were facing constant performance bottlenecks and reliability issues. Their solution was to adopt horizontal sharding, using the user ID as their primary shard key. The strategy involved mapping each user's data, including their tweets and timelines, to a specific shard. This was often done using a simple modulo operation, shard ID equals user ID %n, where n was the total number of shards. This approach enabled highly parallel read and write operations for individual users' timelines, dramatically improving performance and throughput. While this initial sharding strategy was highly effective for scaling, Twitter's infrastructure continued to evolve. Over time, they migrated to Manhattan, their custom-built, highly distributed, multi-tenant key-value storage engine, which provides even greater flexibility and scalability beyond traditional sharding. Twitter's journey exemplifies how sharding can be a game-changer for hypergrowth companies. When designing a sharded system, several critical considerations must guide your architectural choices. Choose between range-based or hash-based partitioning. Range-based partitioning divides data based on a range of values. For example, user IDs 1 to 100 in shard 1, 100 and 1 to 200 in shard 2. This is simple for sequential access, but can lead to hotspots if new data is concentrated at one end of the range. Hash-based partitioning, like user ID %n, distributes data more evenly across shards, reducing hotspots, but makes range queries more complex as they might span multiple shards. Keep related data on the same shard. To minimize the need for expensive cross-shard joins, design your data model such that highly related data, for example, a user's profile and their posts, resides on the same shard whenever possible. Monitoring tools are essential to catch shard imbalance. Continuously monitor the load, data size, and performance of individual shards. Early detection of data skew or hotspots is crucial for proactive rebalancing. Backup and failover must be per shard, not global. Each shard needs its own robust backup and recovery strategy, independent of other shards. This ensures that a failure in one shard doesn't bring down the entire system and recovery can be isolated. Always plan for resharding from day one. Assume you will need to reshard at some point. Design your architecture with mechanisms to facilitate data migration and remapping of shard keys with minimal downtime, even if it's a complex undertaking. To summarize our deep dive into database sharding. Database sharding is a non-negotiable, must-know technique for achieving real-world backend scalability in high-traffic applications. You are now familiar with the main types of sharding: vertical, horizontal, and directory-based, each serving different partitioning needs. You understand that the choice of the shard key is paramount, directly impacting performance, data distribution, and future flexibility. Twitter's journey serves as a powerful, large-scale example of how horizontal sharding can transform a system's ability to handle massive growth. A deep understanding of database sharding is not just an interview booster, it's a foundational element of the system architect mindset, enabling you to design resilient and scalable distributed systems capable of handling millions of users. Before you go, I'd love to hear from you in the comments. If you found this video helpful, do give it a like, share it with your friends, and of course don't forget to subscribe to the channel to help us grow. I will see you in the next one. Till then, happy learning.